Hello guys, welcome back to my channel Gamma Di Gamma. So in this video I'm gonna solve MIT Integration B Final 2020 questions, and like before I'm gonna split this up into two parts. So part 1 will have the first 5 questions and then part 2 will have the remaining 5. Now before I start, I must confess each question required the participants to sort of solve it in 3 minutes. Now I will confess I don't do really well under time pressure, and that's why, so if you think I'm smart enough, I was good enough to participate, please. I also did not get all of them. I struggled with only one of them. The rest were pretty easy under the no time constraint way that I solved this in. So let's get started. Questions are pretty interesting though, so that's why I'm doing this on my channel. Number one was just simplify this integral I. Integral from 0 to 1 dx over alpha x plus beta times 1 minus x, the whole thing squared. Now a natural thing to do would be to look at the x and the 1 minus x and then do an appropriate trigonometric substitution. So x is sine squared theta, because then 1 minus sine squared will be a cosine squared. We can use that nice property. Dx, notice, is going to be 2 sine theta cosine theta d theta. So I in all is integral from 0 to pi over 2. Verify this yourself if you want. 2 sine theta cosine theta divided by, let's see, alpha times sine squared theta plus 1 minus sine squared theta, as I said, is cosine squared theta squared with the d theta. Well, what are we gonna do now? What we can do now is divide by a cos to the fourth. So what that will do is, if we divide by a cos to the fourth, so I have this. So assuming I have a cos to the fourth, I can write one cos here and then a cos cube there. I have to do that with the denominator as well. In the denominator, I'm going to skip some steps. The cos to the fourth goes inside the square. So we have sine squared over cos squared, which is tan squared theta plus beta squared. And then we can simplify the numerator a little bit more. 2 times, I believe, tan theta, yes. And then here we have a secant squared theta divided by nothing else changes. So alpha tan squared theta plus beta squared d theta. Now we can do another nice substitution. U is alpha tan squared theta plus beta, the denominator basically. What that allows us to do is, since we have the derivative in the numerator, so we have the derivative of this is going to be 2 alpha tan theta secant squared theta d theta. We have everything except the alpha, so we can just divide that out. 1 over alpha integral. Well, when theta is 0, u will be beta. And then when theta is pi over 2, tan of pi over 2 will be infinity, and plus beta is still infinity. And here we have du divided by u squared, which is a pretty trivial integral to do, minus 1 over u evaluated at infinity and beta. The infinity bit goes away and we just have 1 over alpha beta, and this is indeed the simplification for this integral. So there we go, we've solved question 1. Now a fresh question, question number 2, was relatively straightforward. So e to the 2x and inverse tangent of e to the x dx. We can do one quick simplification. E to the x inverse tangent of e to the x e to the x dx, because if we use u is equal to e to the x, giving us du as e to the x dx, we can write everything as u inverse tangent of u and du. Well, now the clear answer to approach is integration by parts. So we're going to integrate the u while we differentiate the inverse tangent. U squared over 2 inverse tangent of u minus u squared over 2 over, now we differentiate, we get 1 plus u squared du. So we can sort of factor this out, add a 1, subtract a 1. So since we just have a u squared, if we add 1 with a minus 1/2, we can subtract 1 to give a net 1/2 du over u squared plus 1. This is nice because we can evaluate everything we have here. This is just 1, so we have integration of 1, so that's u over 2 plus 1/2. Notice this is the antiderivative of inverse tangent of u plus c. Now we can just back substitute u as e to the x, so we have e to the 2x plus 1 over 2 times the arctangent of e to the x minus e to the x over 2 plus c. There we go. That wasn't too bad, was it? Question number 3 now. Now I will confess, this was that question that I really couldn't figure it out in one go. I had to sort of reverse engineer in some ways, not completely. I had the right idea, but I just didn't go forward the algebra. I did not have faith in the algebra. So it looks like this, and then it has a crazy denominator, plus 2021 cosine x squared dx. Now, one basic strategy is u substitution. That does not directly work in this case because the antiderivative of the denominator is nasty, I mean the du factor, if we take u as the denominator, is going to be pretty nasty. So what we try to do is we try to sort of factorize the numerator in terms of the denominator. Here it's not going to be a complete multiplication kind of factorization. There's going to be a difference. One useful identity we can use is sine squared x plus cosine squared x is 1. So whenever there's a 1 in the numerator, so there's a 1 for x squared, there's a 1 for this 2020 times 2021 factor. And we have x sine x, if we factorize it in terms of the numerator and of the denominator, we have this. So if you want to generate a sine squared, because we want an x squared, right, we need another factor like that. So we need x sine x. So if they multiply, we're going to get a x squared sine squared. We also need a 2020 cosine x, because we want a 2020 times 2021 cosine squared x plus cosine squared x. But the issue is this will introduce some cross terms, and not to mention that we're still missing the x squared cosine squared factor and the 2020 times 2021 sine squared factor. For that, we're going to have to subtract a few things. And why are we subtracting particularly when we could technically add? You'll find out is because we can't cancel the cross terms if we don't subtract. That's one reason, but another reason is will be evident shortly. I don't really appreciate this question because it's sort of kind of a lucky guess. There's no one clear approach that anyone can use. And then we still have to divide by the denominator, which was just observing all this time. With the dx, we have to move this to the other side a little bit more. Okay, fair enough. What that gives us, well, first of all, let me just label a few things here. I'm going to label f of x to be basically the bit in the denominator. So x sine x 2021 cosine x, and g of x is the other guy. So it's minus x cosine x plus 2021 sine x. Why is this useful? Because if we differentiate f of x, so we get f prime of x, we're gonna get minus I think I switched the labels around. I should be a little more consistent with my work. So this is g, that's f. So if I say f prime, I'm gonna have minus cosine x plus x sine x plus 2021 cosine x, which basically becomes x sine x plus 2020 cosine x, which is exactly the factor that was alongside the f of x in the first term. Now the similarity doesn't end there. G prime of x is going to be x cosine x plus sine x minus 2021 sine x, which turns out to be x cosine x minus 2020 sine x. Now this is really useful, at least this labeling was useful, because now we have f of x times g prime of x minus g of x f prime of x divided by f of x squared integrated dx. What is this? This looks like the quotient rule, does it not? This is d over dx of g of x over f of x. Actually, there's I kind of messed up my notation slightly. So we have, let's see again, x sine x. So there's g of x f prime and a g prime f. Okay, so we have, and then a g of x squared. Apologies for that goof up. And that's simple, right? Fundamental theorem of calculus. So what's f of x? We know that, we label that. Minus x cosine x plus 2021 sine x divided by x sine x plus 2021 cosine of x plus c. There we go. This horrible integral has this answer. Yeah, this was one of those questions that people with a good eye or good mental algebra skills can sort of have an idea of how to solve this quickly. We move on to number 4. So for number 4, we have, it's a limit actually. Limit is n goes to infinity. Integral 0 to infinity x minus 1 to the n e to the minus x dx divided by integral from 0 to infinity x to the n e to the minus x dx. Well, one thing to do is we can simplify the numerator a little bit. So u is x minus 1, du is dx. We have limit as n goes to infinity. Integral from minus 1 to infinity u to the n e to the minus u minus 1 du divided by integral from 0 to infinity x to the n e to the minus x dx. Okay, so now we can still simplify a little bit more. The e to the minus 1 will become 1 over e. Limit as n goes to infinity. We can definitely split the integrals over the range from 0 to infinity. Let me shift this down. Have more space. So 0 to infinity u to the n e to the minus u du, integral from minus 1 to 0 u to the n e to the minus u du. Everything is divided by integral from 0 to infinity x to the n e to the minus x dx. Now, one thing to notice here is that the first term will actually tend to 1 because it has the same functional form. Instead of x, we have a u on top, so that doesn't matter because it's a definite integral. The second term, actually, we need to do a little more work to show that it sort of goes to 0, and it does. Spoiler alert for that. So let's do an analysis kind of argument. So we have limit as n goes to infinity, absolute value of integral minus 1 to 0 q to the n e to the minus u divided by integral from 0 to infinity x to the n e to the minus x dx, and there's a du I forgot there. Well, the denominator is actually gamma of n plus 1 if you observe closely enough. Gamma of n plus 1. So there, at least we're getting rid of some integrals. We can use the triangle inequality for integrals to get sort of shift the absolute value inside. U to the n e to the minus u du. The integral is pretty much finite, at least the bounds are finite, so we don't need any dominated convergence or anything like that, at least for now. Well, u to the n has an upper limit in absolute value of 1. So we can just sort of get a less than or equal to, again, e to the minus u du. I lose the absolute value because exponential function is always positive. Gamma of n plus 1. So is gamma of n plus 1 because it's sort of really, really large because it's a factorial. This actually turns out to be limit as n goes to infinity 1 over e minus 1 over gamma of n plus 1. Well, the gamma of n plus 1 is unbounded, and in the denominator it will make the entire thing go to 0. So what this is telling us is that this second term is going to 0 while the first term remains 1 over e, limit as n goes to infinity of integral from 0 to infinity u to the n e to the minus u du, or gamma of n plus 1 is 1 over e, limit n goes to infinity, gamma of n plus 1, same thing as in the denominator. This goes to 1 for any n, so we have 1 over e as the final answer. Now I think they probably didn't need this kind of justification on the exam, but I think this is the most clean kind of solution I can present to you guys since we're doing this on my channel. This argument here of sort of using these inequalities and bounding it on top by 0, they're really, really nice, and you could use epsilons, deltas, and make the argument more rigorous, but it doesn't really matter here. We still did it. Yeah, we still did it. Last question now for this video at least. So finally moving on to number 5. We have integral from 0 to 6 of the cube root of x plus cube root of x plus cube root of x till infinity. So it's one of those classic infinite radical Olympiad kind of problems. There's one clear strategy to do these kinds of questions. Take a variable, say u, set that equal to the infinite radical, and this is really useful because u cubed is going to be x plus the infinite radical again. So there's this nice recurrence thing with infinite radicals, which is u cubed is x plus u. X is u cubed minus u, which means dx is 3u squared minus 1 du. Now there is a question about the upper and lower bounds. So what do we do about that? Let's see. So when x equals 0, that means x is u cubed minus u, right? That's u times u squared minus 1. I'm factorizing it. Equals 0. So that happens when u equals 0, u equals minus 1 or plus 1. We don't know which one to choose. 0 is tempting, but that's not right. When x equals 6, we have u cubed minus u equals 6. And considering this appeared on this integration b, which had a small time limit to it, the solution for this equation was pretty simple. That's u equals 2. Unique solution, at least the integer solution that we know. The unique integer solution, I think. Yes. Now, which 0 do we choose? Well, look at the behavior. This is a cube root function, right? The original integrand is a cube root function. A cube root function is always positive and it's always increasing like this. Now our function u cubed minus 1, well, we know the zeros. There's 1 0 at minus 1 and 0 and 1. So let's say this is -1, this is 0, and this is 1. You can plug in 1/2 in u cubed -1 to basically give you something that's negative, which means it's negative in this region here. It's negative in this region here. By continuity, it's positive here. Again, by continuity, it goes like this. So this is what at least the cube root function looks like. Near the roots. So if we chose root, we know one of them is one of the values. It actually doesn't go down. Again, there's no other root. So it just keeps going positive. So say 2 is here. Well, if we choose 0, well then the function will have to decrease in the 0 to 1 region, and that's really not plausible, because we know the growth, we know what the original integrand is, or what it graphs to be. It's this this growing function that's positive. So 0 is sort of out of the question. You can use the same argument for -1, because although it does grow, it does fall as well between 0 to 1, because you're always going to cover that as you get to 2. You're always going to sort of go through that value of 0 to 1 when we're going to 2, because we know the top bound has to be 2, just because it's the unique integer solution. Maybe I should draw this more carefully. It's increasing. So -1 is out of the question because it decreases in that value of 0 to 1. And the best candidate we have is 1. So the integration is actually going from 1 to 2. And we replace everything. Well, this guy was u. Dx was 3u squared minus 1 du. And this is integration is really trivial. Evaluated at 2 and 1. So at 2 we have 16 minus 4 by 2 minus 3 by 4 plus 1 by 2. This is 12 minus 2 minus 1/4, which is 10 minus 1/4, which is 39 by 4, and that is the right answer. So there we go. I just analyzed behaviors. This is probably a crude argument, but it works because of the growths of original integrands and integrands after substitution. So yep, that's it for this video. We'll do questions 6 to 10, the remaining 5 questions of this integration B final, in the next video. So see you then. Peace out.